Hi again, everyone. We have an interesting problem in front of us about how to find the volume of a torus. In case you haven't heard that word before, a torus is a fancy word for a donut, so a mathematically perfect donut. And the recommended way to tackle this problem, at least the calculus way, is to think of a donut as being a solid of revolution swept out by this circle. Right, so this circle you're thinking of as filled in, and you imagine revolving it around the y-axis, and perhaps you can imagine that would actually sweep out a donut shape. We're going to do this in general, which means our donut is going to have a certain, we'll call it like the big radius here. So that's the distance from the origin to the center of the circle, and a certain small radius, which is the radius of the circle itself, which we're calling little r. So I've just gone ahead and noted that this is the point capital R comma little r. Similarly down here. And we're going to use some calculus techniques to integrate this thing, slice it up, and then calculate the volume. Right? Okay, so first of all, how are we going to slice it? Well, it might help if I sketch what the solid of revolution will actually end up looking like. So there we go. There's a circle. I guess I could make that a little smaller. There we go. So that's what it looks like when it reflects across the y-axis, and then actually revolving this thing, it'll sweep out something like this. Not drawing it great, but well, something like that. So some donut shape where, like, indeed, I guess I could draw this in as well. Okay, so hopefully that looks like a donut to you, like a see-through donut. I guess I could even, if I wanted to, draw, here's a little slice of the donut as the circle revolves around like 90 degrees. Here's another little slice. Okay, so that's as nicely as I can draw a see-through donut. And what we want to do is slice this thing up in some nice way to make it easy to integrate. And the thing to think about, what's the best way to slice it? Well, you could imagine that, if I cut it just straight down the middle, right down the x-axis, then I would actually get something that looks like this. Which is, it's basically like, I'm calling it a donut, but imagine it's a bagel, right? So you get the lower half of a bagel if you slice it there. And so that's nice, right? The cross section of a bagel, just this little section right here, is a washer. Or you might call it an annulus, whatever you prefer to call it. It's something we know how to integrate, right? So slicing this bagel up into a bunch of little washers makes me end up with, something like this. Here's my littlest slice of the bagel. So you get a whole bunch of stack of those washers making a whole giant bagel. Anyway, the thing we need to know if we want to figure out the area of a general slice here, the washer part of it, is we need to know the distance. So this point in red I just drew is sort of like the origin here. And we need to know the outer radius and the inner radius. So the outer radius is sort of this distance, because you're imagining, looking at it straight down, it looks like this. And so that's the outer radius. This is the inner radius. Okay, so inner radius is going to be this guy. So how do we figure those out? Well, looking on the larger diagram, it's actually going to turn out that this outer radius here of the washer is exactly this function, or this arc of the circle that we started with. Maybe you can see why, but either way, then the inner radius is going to be the other part of the circle. Again, maybe you can see why. It's sort of because as you're sweeping this circle out, right, so going back to this and imagining rotating it around the y-axis, well, sure, like this actually gets sent to here, gets sent to here, gets sent to here, right? It does form the outer disk of like any washer I draw in here. It's the outer boundary. Whereas the inner circle here, the inner half circle, traces out like this portion, this portion, this portion. And that's exactly, you know, that's exactly the inner radius we're looking for our washer. Okay, so then it comes down to, let me re-sketch this diagram. Straighter. Cool. So let's draw this starting circle again. Okay. So the thing we have to find, the reason I put these points on here to begin with, is we have to find an equation that describes the right half of the circle and the left half of the circle. Maybe you've done that before for like top half of a circle and bottom half of the circle. You can do something entirely parallel for the right and left halves. And all we need to know is the general equation of a circle centered, in our case, at capital R, so that's sort of capital R comma 0 in the xy plane, of radius little r, right? Because that's this distance here. Okay, well that, you may recall, you can just write it as x minus the x coordinate of the center squared plus y minus the y coordinate of the center squared equals the radius of the circle squared. And then the thing you usually do at this point is solve for y to get like the top half and the bottom half of the circle. However, you may notice that this arc of the circle is not a function of x. So if I solve for y and get something in terms of x, it wouldn't be correct, right? This is not a function of x because it doesn't pass the vertical line test, for example. But it is a function of y in the sense that if I turn my head 90 degrees and think about it sideways, it does pass the sideways vertical line test. So that should tell you I can get away with solving for x here. Okay, so x minus capital R squared. This piece is just y squared, so let's subtract y squared from both sides. Let's take a square root. And again, you have to be careful to include plus or minus when you do that. Sorry about that. R squared minus y squared. And then add the r to both sides. Lo and behold, you get two solutions. If you take the plus, you get the right-hand side of the circle. You can confirm that if you want to like plug some numbers in. If you take the minus, you get the left-hand side of the circle. And just keep in mind, the right half of the circle is our outer radius. So thinking about this now in terms of volume using the washer method, let's just recall the formula. There are a couple of ways to write this, but I'll just write it like this. Pi times the quantity outer radius squared minus inner radius squared. And for us, we're slicing the bagel along the y-axis to get all those washers, so dy. Okay, so what are A and B in this case? Well, that's sort of asking what's the lowest point I can slice the bagel. Looks like it's right around there. That's why I put this negative little r on here. That's as low as I can go. And as high as I can go is capital little r. Right, so those are my bounds when I slice this thing along the y-axis. And in fact, I mean, there's a pi here. Let's move it out front just to be nice. And then, okay, this is going to look kind of ugly. For now, let's just keep it as outer squared minus inner squared y. And then let's try to simplify the integrand a bit, or not the integrand, but the bounds on the integral. What do we know about bagels? We know that if I slice it perfectly in the middle, I get two equal halves. Right? The top half of a bagel is exactly the same volume as the bottom half of a bagel. Right, so that goes to say, instead of integrating from negative r to r, what if I just integrate from 0 to r? So that'll get me the top half of the bagel. And then if I double it, I'll get the bottom half. Should work, right? It's symmetric, so it'll make our life easier to plug in 0. So let's do that. Now, outer, I said, was going to be, if you take the plus here on the right-hand side, so outer squared is going to be r, big R plus square root of little r squared minus y squared. So I square all that. And then inner is going to be if I take the minus sign over there. So minus square root of little r minus, okay, there we go. Still with respect to y. And I mean, this looks terrifying, but it works out rather nicely. See what I mean? If you were to, so you'd have to FOIL each of these terms, right? And in the process of FOILing, I'd get a positive r squared on this one, and I'd also get an r squared on this one, but then I would subtract them. So those terms will cancel. I don't even need to write them. Similarly, when I do this term times itself, the square root goes away and I just get little r squared minus y squared. Same story here. I'd get a little r squared minus y squared, and again, I'd subtract them. So those terms go away. The only terms I have to care about are like these two things. And certainly when I do that, when I FOIL it out, I get 2 of them for each. So over here, I'll get something like 2 capital R, little r squared minus y squared. Then I have this minus, and this would be minus 2r square root little r squared minus y squared. But I mean, look at these two things. They're exactly the same. Minus a minus is a plus. So I'd actually get 4 of those instead of 2 of them. So let's go ahead and erase this. Change this 2 to a 4. I don't even need the parenthesis anymore. Dy. All right, fantastic. So this looks much more manageable. Remember, we're thinking of capital R as a constant. 4 is also a constant. You can bring both of those out front. So 4 times 2 is 8. And I have a pi and a capital R. Integrating from 0 to little r, this expression. And at this point, you can take one of 2 paths, right? So maybe I'll say method 1. Method 1 is if you just look at this and just think, okay, I'm going to keep doing math. I'm not going to think about the context. And method 2 is you think about the geometry behind the problem and actually think about the integral being area under a curve and think about what this curve looks like. Get some geometric intuition behind it. I'll show both. So method 1 would be trig sub. Right? This is the square root of something squared minus your variable squared. So that's a classic example of, I guess, sign substitution. So let's write this in. Let's just say, normally I'd write x equals a times sine theta, but this is y in this case equals, my constant here should be then r sine theta. Okay. And then you should figure out dy as well, so you can plug that in. So dy would be r cosine theta, d theta. And so making that trig sub would get me to, okay, I'll leave the constants alone. Let's just forget about our bounds for now. Right? I'm going from 0 to r when I'm using the variable y, but now that I'm changing to theta, it'll be something else. So let's just forget about them for now. We'll come back to that later. And this would simply look like r squared minus, okay, y squared would be r squared sine squared d theta. And this will work out sort of nice. Each of these terms has an r squared. So if I factor that out and pull it outside of the square root, it would just come out as a little r. And again, little r is a constant, so why not move it out front? And I would be left with just 1 minus sine squared. But okay, trig identities say 1 minus sine squared is cosine squared. And okay, I have cosine squared under a square root. I guess technically that's absolute value of cosine, but it's not going to matter for us. Let's just call it cosine. Okay, so classic example of trig sub. Integral of cosine is sine. So this gives me sine of theta. I'm not going to write a plus c because technically we do have bounds. I just said we'd ignore them and get to them later. Particularly, we want to get to them when we get everything back in terms of y. So, okay, what is sine theta? Well, this is one particularly nice instance, right? Sine of theta, I don't even have to draw a triangle for this. It's just y over r. So, great. This is 8 pi capital R times little r. Y over r. Now that I have y back in here, I can sort of plug in my bounds, but I guess first let's cancel these little r's. So this really would have just been 8 pi capital R y, and plugging my bounds back in that I forgot about, 0 and r, then we get this. So no, I forgot about something. Haha, I knew this was too simple. Okay, I forgot to put the d theta in. Good job to you if you caught that. Or forgot to put the dy in. So let's go back a step. I knew it should have been uglier. So cool, dy should have had an extra r cosine theta out here. There we go. And so, I mean, this will still be r cosine theta as well. So I get r squared out here, cosine squared. Cool. Okay, so that's a little meaner to do. Cosine squared we can use a half angle for, so we know that this will keep the same. The half angle formula for cosine is the one that has a plus on it, so it's plus cosine 2 theta d theta. Cool. And then I could pull that 1/2 out. So 8 times 1/2 is 4. This is looking more like what I expected it to look like. And then let's just really quickly integrate this thing. So integrating 1 gives me theta. Integrating cosine 2 theta gives me positive 1/2 sine 2 theta. Then, okay, I can convert this back into y, which I do need a triangle for. So before I do that, I guess I could say it might be nice to use a trig identity. So theta plus, so there's a trig identity that says this is actually just sine of theta cosine theta. So sine theta cosine theta. It's more like it. And then this will end up being pi r squared. All right, so what is theta going to be? Let's draw a right triangle. Okay, so we want it to be true that y equals r sine theta. Another way of saying that is sine theta should be y over r. But sine is opposite over hypotenuse, so we get that. Pythagorean theorem says this should be r squared minus y squared. Okay, so in here we get theta. Let's just come over here. So sine of theta we know is y over r. So that means theta is arcsine y over r. Cool. And then from the triangle, we can get cosine. So cosine's adjacent over hypotenuse, which is this. Okay, so pretty hideous. Theta, so we get arcsine y over r. Surprisingly, that'll work out nicely. Plus sine theta times cosine theta. So that's y over r times that. So that's y times this. Sorry, I'm writing so tiny. Okay, and then we can put our bounds back on from 0 to r. If we plug all this in, I will scooch this over a bit. If we plug all that in, let's just talk about it. If I plug in r, I get r over r, which is 1. And then we ask ourselves, okay, when is sine equal to 1? That happens at pi over 2, I suppose. So great, we get pi over 2 for that. And then if I plug r in here, guess what? Under that square root, I get r squared minus r squared, which is 0. So that goes away. So I just get a pi over 2. If I plug in 0, I get arcsine of 0, which is 0. And if I plug in 0 to this one, I get, yeah, I got 0 again. So lo and behold, a lot of things turn into 0 except for that pi over 2. So you get 4 pi capital R little r squared times pi over 2. And if we simplify that, we get 2 pi capital R little r squared. Oh, okay, that was a doozy. There's a much easier way to get there. There are actually 2 much easier ways to get there. So let's see one of them. Now that we've done it the brutal way, we'll go back and do method 2. I mean, you know it's the brutal way if I made a mistake during it. So method 2 says, instead of fiddling around with the trig sub, I should just think about this function. Right? It's a function of y. And in fact, I mean, that looks like it looks like what you would normally think of as the upper half of a circle. But since it's in terms of y, it's the right half of a circle of radius r, centered at the origin, right? And we're saying that we're going to slice this up along the y-axis, but in fact, we're only going to slice up from y equals 0 to y equals r. So we're only slicing up this portion. So thinking about it as area under a curve is equivalent to thinking of it as the area of a quarter circle of radius little r. And that area of that quarter circle should be 1/4 pi r squared. So that's way easier, right? So this would be, writing it out, 8 pi capital R. And then this whole integral just becomes 1/4 pi r squared. That, oh, sorry, I just noticed down here, we had 2 pi's. I forgot to write pi squared. Anyway, minor error. 1/4 times 8 is 2. Again, we have 2 pi's, so that's pi squared. Again, we have an r, and we have a little r squared. Okay, so sometimes trig subs can be realized geometrically, and you don't have to worry about actually going through the process. But there's a third way to realize what this is, okay? How could we have skipped all of this integration to begin with? Well, here's the kicker. This could be rewritten as 2 pi capital R times pi little r squared. Maybe some of you saw that already. If you did, kudos. What you should recognize here is this is circumference of a circle with radius capital R. This is area of a circle with radius little r. So why does it make sense to be multiplying a circumference of a circle with one radius times the area of a circle with another radius? It's because if we go back to our diagram, let's forget about the bagel over here. If we go back to our diagram, let's mark some things up here. In purple, filling this in and asking what the area is, well, this circle had radius little r. These were negative r and positive r. And so this area is actually pi little r squared. And what did we do with that circle? We revolved it around the y-axis. So if you watch what happens to this like center point, the center of the circle traces out a circle as it goes around the y-axis. Right? So we had drawn previously that like, okay, there was a circle here, and you connected it up, and it ended up looking like a donut and all that good stuff, right? But okay, this like red thing is like the center of the donut. It's the best part. Probably the outside with all the glaze and good stuff is the best part. Anyway, it's the doughiest part. This doughiest part, the circle that gets traced out, you could ask the question, what's its circumference? And sure enough, if I didn't draw over it here, this was capital R is the radius of that circle. And so the circumference would have been, C would have been 2 pi capital R. So looking from here to here, you're like, oh man, both of these things appear in the diagram. Why does it make sense to multiply them together? Well, it's like saying, imagine your donut or your bagel wasn't yet cooked. Maybe it was still made of dough, right? And if it's still made of dough, I could slice a little part of it. I could, slice it here and unroll it. And if I unroll this thing, then all of a sudden it's just a tube of dough, like a cylinder of dough. Let's draw like this with dotted lines, where this still has radius little r, draw it like that. And since I unrolled it, that central like red circle is actually this, right? This length is 2 pi r, capital R. And so if I asked you to integrate this thing, if I asked you to find the volume of a tube, that's a much easier question, right? That's much easier than asking what's the volume of a donut, but it comes down to be the same thing in the sense that you could have just added up a bunch of circles like this, and this is pi r squared. So extruding that purple circle across to get the volume, I mean, you literally just multiply these two things together. Okay? This is like the height of a cylinder. It's base times height. And there you go. That's 2 pi r times pi r squared. That's exactly what we ended up with in both cases, aside from the little typo I had earlier. But written like this, you can actually realize it as some geometric thing. So no calculus required. All you have to do is think a donut could be unrolled, and then it's just a circle times the area of a circle times its circumference. Anyway, that's all. It's one of my favorite problems. Thanks for watching.